Hello, we'll step forward to the sixth part of today's webinar. It will be the last part for today. It regards retaining structures, and the speak will be given by Mr. Luigi Callisto. He's a full professor at the Geotechnical Engineering at the University of Roma, Sapienza Università di Roma. He's a well-known researcher in the field of soil mechanics and geotechnical earthquake engineering. He has theoretical as well as laboratory experience, and his recent research activity concerns performance of deep excavation seismic design of earth retaining structures. Thank you very much, Professor Callisto, for your presence today, and please, you may start your speech.
Thank you for your kind presentation. Good morning, everybody. This is a brief outline of my presentation today. I will be making some introductory comments about displacing and non-displacing rotating structures and about the application of force-based versus displacement-based approach. In fact, most of the presentation will be addressed to the application of force-based approach to displacing and non-displacing structures. Whereas today I will not be covering some specific cases, including the code that you see listed here. In the last part of the presentation, we will address briefly the implementation of the displacement-based approach for retaining structures. Now, the distinction between the displacing retaining structures and non-displacing retaining structures really has to do with the possibility of some retaining structures to accumulate displacement having a weak side, a weak direction. So in fact, even for asymmetric seismic actions, displacement will be accumulated towards the weak side only. Whereas this is a non-displacing retaining structure, because if we take the view that the structural members should remain in their elastic range, if a structural member does not yield here, these retaining structures really cannot go anywhere, so they cannot accumulate the displacements. And just to be clear, this is a non-displacing retaining structure. These are two displacing retaining structures because, of course, they're not connected to each other. The verification of retaining structures, the seismic verification of retaining structure, should take into consideration the residual displacement of the structure and the internal forces in the structural members. Now, these two requirements have somewhat different declinations when we come to force-based approach or to displacement-based approaches, because in a force-based approach, we do not calculate explicitly the displacements. So the displacements are really related implicitly to our equivalent seismic actions, as we will see in a while, whereas we do calculate directly forces in structural members, being a force-based approach. On the other hand, in a displacement-based approach, usually we will be calculating directly from our modeled displacements. And as for the forces in the structural members, they may or may not derive directly from our calculation model, depending on what model we will use. Let's concentrate now for a while on displacing retaining structures, and let's see how do we compare capacity and demand. But firstly, how do we define capacity and demand for these structures? In fact, capacity is defined as the critical seismic coefficient. What this means that if we consider a certain retaining structure, we imagine to load this structure with equivalent inertial forces, function of an increase in acceleration, and imagine to monitor the displacement of these structures at a certain value of the acceleration, we will attain a plastic mechanism. So in fact, the critical acceleration is one that corresponds to the attainment of the capacity of the system. On the other hand, the demand is related to the maximum acceleration, but this is reduced or can be reduced according to the two factors that you've seen already, that relate really to the non-synchronicity of the seismic motion and to the nonlinear behavior that is the possibility of accumulating displacement. How do we calculate this capacity, this critical seismic coefficient? Well, being the resistance of a plastic mechanism, we calculate this capacity with the basic ingredient of analyzing a plastic mechanism, namely equilibrium and compatibility with the strength criteria. Equilibrium is expressed in terms of total stresses, whereas the strength criterion should be expressed in terms of effective stresses. A couple of additional comments on this. One of the comments is why do we express the capacity as the critical seismic coefficient? We do the same for slope stability, as you have seen. A reason is that the main reason is that different retaining structures may activate a different plastic mechanism. And in fact, the same retaining structure may activate different plastic mechanisms. For instance, the wall may slide, we may have very capacity, we may have overturning, we may have a general instability. And each of these mechanisms will have a different critical acceleration. But of course, the mechanism that will dominate in the accumulation of displacement will be the weakest one. So in fact, by specifying the critical seismic coefficient is the capacity, we do not have to engage in a long and cumbersome list of possible limit states or plastic mechanisms depending on the type of retaining structure. Another point that it is important to address is why do we advocate for retaining structure and effective stress approach? Meaning that the strength criterion should be expressed in terms of effective stresses. Of course, we do acknowledge that saturated soil will deform under undrained conditions during the seismic motion. However, we must remind that the excess of water pressure induced in the soil during the construction, by the construction stage, which for excavations, for instance, are very, very important, they are no longer there because they have decayed, because consolidation times are usually much shorter than the long flow-time period associated to important earthquakes. And therefore, the structure itself will be initially in a drained state with effective stress state, which are very different from the initial one. Usually, effective stresses will have reduced, and therefore the undulation strength obtained from site investigation will no longer be applicable. In fact, it will be too large. And there is also another reason, is that the solutions for the active and passive pressure expressed in total stress, including the inertial forces, they do exist, but there's not many of them, but they do exist, but they are not particularly robust, and they are quite difficult to implement in many practical cases. So the contact pressures that we need against the wall, that we need for equilibrium, they should be defined as sum of effective stress under limited condition plus pore water pressure. And you may notice that pore water pressure here is entered in a couple of instances. The pore water pressure decreases the vertical effective stresses, and then increases the horizontal effective stresses to get the total stresses. But there is also a third effect of the pore water pressure, which is somewhat hidden in the nature of the air pressure coefficients here. And I'll try to explain this. Here, for instance, we are in the limit passive condition. And if we, so the unfavorable direction of the inertial forces is this one. If we combine the vertical body forces with the horizontal body forces, we have a resultant vector of the body forces, which has an inclination over theta, theta being just the arcotangent of the horizontal seismic coefficient. Now, if we consider a reference horizontal plane at the same depth, we will have a shear stress on this horizontal plane as an effect of the inclination of the body forces. And in a Morse circle, the point representing the stress state on this surface will be lying on a line inclined by theta. But if we have a pore water pressure, this point moves leftwards, and therefore it will be located on a line inclined by a larger value of theta. This is the reason why the presence of pore water pressure causes can be regarded as causing an increase in the equivalent inclination of body forces, and this factor that multiplies alpha h is the ratio of the total to the effective vertical stresses. This increase in inclination has the effect of increasing the active coefficient of air pressure and decreasing the coefficient of passive pressure. Now, the good news here is that for a given value of the horizontal acceleration, the increase and decrease of these coefficients with the ratio of the total to the effective stresses is almost linear. So in fact, we may derive this in a couple of points in our deposit, and then we are able to interpolate linearly. I'm presenting a very brief example here. I'm not going to go into the details of the calculation of the example, but they will be left on slides for your convenience. This is a very simple retaining structure. It's an embedded retaining structure, cantilevered, 3.4 meter excavation height, 3.5 meters of embedded length, hydrostatic distribution of water pressure, coarse grain soil with the structure. These are the seismic action. This is the outcrop elastic spectrum. This is the amplified elastic spectrum, being in this case soil category E. This spreadsheet presents the calculation of the active and passive contact stresses, so the total stresses applied by the soil to the wall, when we imagine a rotational mechanism of a rotation of the wall about a point close to its toe. In this configuration, the horizontal accelerations are 0, and this wall is not in equilibrium, because equilibrium means that the resultant of the horizontal forces and on the moment are equal, so this cells should be equal to 1. Okay. Now, if we want to obtain the critical seismic coefficient here, we have to increase progressively this number, probably adjusting the rotation point until we have a translational and rotational equilibrium. So we have two equations in two unknowns, which are solved here with an Excel solver. I'm sorry, it is in Italian, but I think it's self-explanatory. And at the end of the iteration, we have a translational equilibrium, rotational equilibrium with this critical value of the seismic coefficient and this adjusted position of the rotation point. Under this stress contact, the wall is equilibrium with the strength of the soil completely activated. So this is the number that characterizes this plastic mechanism. So this is the capacity. Then we go to the demand. The demand is proportional to the maximum acceleration, but we have to multiply by beta and divide by K. Now, beta is really related to the ratio of the height of our system to a representative value of the wavelength of the seismic motion, the wavelength of seismic motion being evaluated by this expression where Tm is the mean quadratic period of the earthquake, of the seismic action. Eurocode, as you have seen, allows us to calculate Tm as the sum of the coordinate periods. So if I have here my coordinate periods, I have a certain distribution of shear wave velocity, an average value of small strain shear stiffness. I am reducing this value of small strain shear stiffness to account for nonlinearity using this rho here and using this scatter to be on the safe side. I have G equal to 26 MPa. I can calculate lambda being the average wavelength being about 50 meters, and therefore H over lambda, where H is the average value of the height of the soil in contact with the wall, is 0.1, and therefore 0.1, the value of beta is 0.9. Therefore, but this accounting from the non-synchronicity of the seismic motion, I am reducing the maximum acceleration by a factor of 10%. Then I come to the key value. If we take the definition of the equivalent seismic action and we derive the value 1 over key, you may see that the value 1 over key may be seen as equal to the ratio of the seismic demand divided the maximum equivalent acceleration. So if we perform, as we perform the series of parametric displacement calculation using many time histories, we may establish a relationship between the displacements and this 1 over key ratio, which is the ratio of the critical to the maximum equivalent acceleration. And if we start from a given displacement, if we believe in this curve, this abscissa will give us 1 over key. So in fact, this equivalent demand is the critical acceleration of an ideal system which under the same seismic action will undergo a displacement like this. Now, since our capacity is slightly larger in this example than the equivalent demand, this means that our system has a larger critical coefficient, and therefore it will undergo displacement which are somewhat smaller than the one that we have been using to calculate key coefficient. This is the way in which we account for nonlinearity. with the key coefficients. And of course, in order to be able to use key coefficient, we must be in the condition of accepting these displacement ranges. If we really need the very small displacement, we may be forced to use key values smaller than 1, just in very special occasion, which we want our displacing retaining structures not to displace at all. If we apply this to our case, then we have, excuse me, I have a problem with my Zoom here. Then we have, for instance, if we use key equal to 1, we calculate alpha h. I'm using 0.9 for beta h, 1 for key h, because I want to stay in this displacement range. I have a seismic demand of 0.2, a capacity of 0.207. Therefore, my verification satisfied the demand being slightly lower than the capacity. However, if I want to stay in this other displacement range, so if I'm ready to accept this displacement, I go back to my design. I make a more economical design. For instance, here I have reduced the embedded length. I have a smaller capacity, which I recalculated with the spreadsheet, but I also have a smaller demand because I am accepting larger displacement, and therefore my key value is 1.5. And again, the demand is lower than the capacity, and my verification is satisfied. A final check that we must make is about the internal forces in structural members. Now, of course, we must evaluate the demand, which are the internal forces. Our code states that in most cases, if we allow some displacement, we must compute the internal forces assuming a horizontal acceleration equal to the capacity of the system. And then the internal forces resulting from this calculation should be multiplied by an overstrength factor equal to 1.2. Therefore, in our example, these are the contact stresses that we evaluated before under the critical conditions. This is the light blue is the net pressure. If I integrate once this light blue line, I get the distribution of the shear forces. And if I, of course, if I integrate the distribution of shear forces, I have the distribution of bending moments. I take the maximum bending moment, I multiply the maximum bending moment by the overstrength coefficient, and this is my design bending moment for the most stressed section of this wall. For non-displacing retaining structures, really the evaluation of the displacement is not really an issue because this system cannot accumulate displacement, but we must make sure that the internal forces in the structure are compatible. Therefore, most of our efforts here are devoted to the evaluation of the internal forces. And the real point is that it is also said in the code that here the way in which we calculate the internal forces in this condition really is a consequence of the calculation method that we use to evaluate the internal forces under the static conditions when we analyze the construction sequence. So these two are very much related. So for instance, we may have designed our static condition using empirical relationships, using a subgrade reaction method, or using a numerical model of continuum. In the first case, if you use an empirical approach, the only thing that we can do is to apply elastic pressure with guidance given in Annex F, where I call them elastic because they are derived from elasticity. And these are incrementing contact pressure that must be summed, must be added to the ones that occur under the static conditions. If we have been using a subgrade reaction method, we may use the same technique to calculate elastic stress increment as in Annex F and add them to the apply them as added forces to our wall. Or if under the construction our analysis tells us that the soil behind the wall is in a fully active linked state, we may evaluate this soil stress increment by using the difference between the air pressure coefficient under seismic conditions and static conditions, and at the same time reducing the passive pressure condition to its seismic value. If we have a numerical model of continuum that we have used to analyze our static conditions, that we may add the static equivalent inertial forces to the soil volume, meaning that if we have such a calculation scheme, then we may just load this model with horizontal body forces proportional to the mass of the soil and the structure, And when we increase the acceleration, we will be calculating displacements and internal forces in all the points that we want. So when we have reached maximum acceleration, this analysis will give us the internal forces in the structural elements. The last part of this presentation, last 5 minutes, are devoted to some remarks on the displacement-based approach for Earth-retaining structure. In a displacement-based approach, we calculate the displacements, and the calculated displacement are our demand, whereas the capacity is made by the maximum displacement that we are ready to accept. Therefore, in this case, really our computation efforts are really on the demand side to evaluate the demand. Of course, if we have a large model and we are in a condition of expressing the seismic actions with accelerogram and to perform a fully dynamic analysis, as you see here in the part of the text, well, of course, in this case, we are going to have, as a result, the time history of the displacements, the time history of the bending moments, of the internal force in the structure. So this is a self-consistent calculation model. But on the other hand, if we don't want to do that, which is a time-consuming, complicated expert analysis, we may opt for a decoupled approach. In this decoupled approach, we calculate the actions as using free field ground response analysis, and the action being a time history of the acceleration, and we express the resistance of our system through a capacity curve, which is the one that we shown before, characterized by the critical seismic coefficient. The simplest way to perform this calculation is to assume that the capacity curve is rigid, perfectly plastic. In this case, this is the Newmark rigid block approach, in which we neglect the dynamic response of the system before the attainment of the critical acceleration. This is again our example. This is our critical acceleration, and we will have displacements. We will be accumulating displacement only when the seismic action becomes larger than the critical acceleration. Or we may want to take into account the pre-failure deformability of the soil, and in this case, the computation will show a dynamic response of the system before the attainment of the critical acceleration, and the displacement will be much larger. In fact, this is our same structure that this time, instead of giving the displacement of 1 centimeter, it's giving us displacement of 12 centimeters, which are much more in line with the one associated with the key values that I showed you before. Well, in fact, I will not recommend for retaining structure the use of a rigid block analysis in the application of a displacement-based approach, because a large number of experiences show that the rigid block analysis provides displacements which are way too small if compared to those provided by any model that accounts for the deformability of the system before the attainment of its capacity. And in fact, the key values that you find on the Eurocode were calibrated using parametric calculation or linear calculation, in which this deformability of the earth-retaining structure was taken into account in the equivalence with the key values. A very last comment about this decoupled calculation of implementation of the displacement-based approach is that when you we use this decoupling, the calculation of displacements does not give us directly the internal forces in the structure. So we have to go back to our calculation, take note of the maximum acceleration that is attained during the seismic motion. This is information that we have. In this case, it is again the critical acceleration. Go back to our local model to evaluate from that local model of earth-retaining structure the distribution of the internal forces. And I think that is all on my part. Thank you very much for your attention.
Thank you very much, Professor Callisto, for this interesting speech. Let me check the chat. And we have one first question, an administrative one from Mr. Georgopoulos, meaning that the spreadsheet you have shown during your speech would be good for students to play with it. And he is asking if it's available.
In fact, my students play with them a lot. So yes.
Okay,
they are conceived for students more than for designers. Yes.
So I believe you can
Yes,
be in touch.
I will talk with the Rita. Yes. Oh.
Thank you. And then a second question from Mr. Pantelidis from the Cyprus University of Technology. He's asking the following issue. The problems with the monomob Okabe MO method are well known. Very conservative in the active state, non-conservative in the passive state, and a negative root where when the latter happens, the Eurocode 8 part 5 arbitrarily replaces the whole square root with 0. So MO.
Yes. Mononoble, it's the mononoble Okabe. MO refers to the mononoble Okabe method. Now, I have several replies to this. The first thing is that there are many solutions to the problem of earth pressure. Mononobe Okabe being the oldest of these, but there is a whole bunch of solutions. So now, of course, we tend nowadays not to use mononobe Okabe any longer, but use solutions that are based on limit analysis, so on the theorem of limit analysis in perfect plasticity. In Annex F, we give guidance to one of these methods, which is a lower bound approach. This, of course, this may be normative or informative, but here normative or informative really means that it will be attached to the national version of Eurocode or not. But that lower bound solution is not too conservative or not conservative or whatever. It is very, very close to the exact solution. Very easy to show that. And there's been many, many verifications. So no, it's not unconservative, it's not overly too conservative. I don't understand why the writer is making a reference to the mononobe Okabe solution, which is not referred to in Eurocode in this Eurocode anymore. Maybe the draft was not available.
May I, Stelisanos Pantelidis?
Yes, sure.
Yes.
Sure.
You didn't read the whole question. Please read the whole question. I'm referring to the new method of Eurocode 8.
Which is the new method?
The informative one that you told me. The colleague didn't read the whole question that I did. There is more.
I didn't came to it.
And why are you saying that the new method is more conservative?
Okay, we know the problems about the mononobe Okabe solution. STO uses the mononobe Okabe, but with half peak ground acceleration, which partially solves the problems with the mononobe Okabe method.
But on which grounds are you stating that the informative analysis is too conservative or not conservative?
Let me finish. Let me find my question. So my question is, why are we moving to a new method which is even more conservative? Professor Molnakis says this in his paper for the active state, non-conservative for the passive state, and it presents the same negative root problem with a mononobe Okabe method. I will give you one more message. If you perform a finite element analysis or you compare the new method with centrifuge test results, you will see that this is the new method is very, very, very conservative in the active state, and the problem of the negative root is very big.
Excuse me, I understand that you are referring to the George Milonakis solution, right?
Yes, it is his.
No, it is not.
Okay, maybe I'm wrong on this.
No, the solution that we have in the Annex F is the Lancellotto.
Okay, no problem with this. Wrong name. If you perform finite element analysis to compare the new method or centrifuge test results, you will see huge difference, and there is a great finite and the negative root problem.
Excuse me. These two are two separate problems. The first one is that I don't know about the Mikolonowski solutions. In fact, I do know the Mikolonowski solution.
Forget the Mikolonowski solution. Forget it. It was a wrong name. Okay, forget it. About the solution of Eurocode 8, the new one, and its problems that it is very conservative.
No, it is not. I myself have done many calculations, so I don't agree with the result of your calculations. Okay, and we may check our calculations together, but I'm very confident.
Okay, together. I have given a link in my chat.
Yes, but okay, but I will give you a link to a number of papers when this is demonstrated. This is one. The thing about the square root is that all these solutions have a limit in the case in which the horizontal seismic coefficient is equal to the angle of internal friction. Okay. Because when the horizontal coefficient is equal to the angle of internal friction, the entire soil volume becomes in a huge limit state. We cannot go beyond. So the way that we go forward in this case, which refers to very large seismic actions usually, is to assume that in that case, you have an equivalent rotation of the initially horizontal ground surface, and then a part of the soil is really sliding above the wall. That is what is usually done. But it's not a problem of the theory. Any theory will give you, any solution will give you the same problem. It's not Monocabe or Milonakis.
Not any solution.
Oh, yes.
I will be happy to discuss it with you.
Okay, whenever you like.
Okay, thank you very much.
Thank you also. I think we are running out of time, and this was also the last written question in the chat. So thank you once again, Professor Callisto, for the interesting speech.